Quantum mechanics is all about wave functions, probability amplitudes, states in Hilbert spaces, right? Well, not so fast. There is another way which does away with all of this, an algebraic formulation of probabilities, which although physically is equivalent, it's not just some trick. It goes much deeper and might even change what you believe is real, and what actually exists in the universe, not just some artifact of the maths. Merging standard classical probability with the quantum, and applications ranging from quantum statistical dynamics to cryptography, it can do so much more. Welcome to Almost Sure. Let me start by telling you a story. Alice, here she is. She prepares an electron in either the spin up or spin down state. Now, electron spin is a curious thing. They're like little spinning balls, but they're not balls and they aren't spinning. That's how the joke goes, but whatever it is, they do have spin and a magnetic moment which can point in any direction and which can be measured along any axis, say by passing them through a magnetic field and seeing how they are deflected, as with the famous Stern-Galach experiment. And in this case the spin will be found to be positive or negative 1/2. And measuring spins along different directions simultaneously, that's impossible. Because if you measure along one direction, say the vertical direction, it automatically forces its spin in any horizontal axis to be totally random. Anyway, Alice, she tosses a coin. And if it comes up heads, she puts the electron in the spin up state. And if it comes up tails, she makes it spin down. Then she runs away, taking a coin with her. We're left with just an electron, either spin up or spin down, but we don't know which. Well, yet. A simple, random setup. Not even quantum randomness, just classical uncertainty based on the toss of a coin. Next, Bob, he comes along, and he does exactly the same as Alice, but with a twist, literally, by 90 degrees. If he gets heads, he prepares an electron in the spin right state, and for tails he puts it as spin left. Then he too runs away, taking his coin with him. And that's it. 2 electrons, one from Alice, which is either up or down, and one from Bob, which is either right or left. They are clearly different. Spin up electrons are different from spin left and from spin right, as are spin down electrons. But how can we tell the difference? Well, here's the clever bit. We can't. Measuring either electron along any axis will give a 50% probability of positive or negative spin. In fact, there's no experiment that can be performed that will ever detect any statistical difference between these 2 electrons whatsoever. Now this has some far-reaching consequences. In terms of quantum states or wave functions, the 2 electrons are different. Different wave functions, spin up is different from spin right and so on. But although they are different, Alice and Bob's electrons are the same. Well, maybe wave functions are not fundamental. And also once you mix classical and quantum probabilities together in the same system like this, they can't be disentangled. So maybe they're not even separate concepts. Like space and time in relativity. Classical and quantum probabilities seem different, but combined together, they can't then be decomposed in any unique way. But this is not just some curiosity, it has applications to quantum cryptography. Suppose we want to create a digital key, a random sequence of binary bits, 0s and 1s, and share them with a friend, so that we can then encode and decode messages sent between us. But it's very important that no one else can get hold of them, otherwise they could decode and spy on all our secret communications. Well, encode them in the spins of electrons, up or down, like Alice, or left or right, like Bob, and choose between these randomly and send the electrons. But our friend wouldn't be able to distinguish Alice and Bob's electrons. They would just have to guess and measure horizontally or vertically, at random. After this, we can then just announce which were horizontal and which were vertical. So our friend just keeps those which were guessed right, and now we both know these random digits or coin tosses from the directions of the electron spin, and we can use these for the digital key. But the cunning thing is, if anyone had intercepted the electrons and measured the spin, this could be detected. It's impossible to measure the spin without affecting it along other axes. So we just agree to compare some of the digits with our friend to see if they agree. If they don't, someone has been snooping. And this is the idea behind BB84, one of the first ever quantum key distribution schemes. I'll start with a brief recap of the standard Hilbert space approach. Now, this approach to quantum mechanics using Hilbert spaces, wave functions, probability amplitudes and so on, this has been standard stuff for nearly 100 years now. And with good reason, it works well. But it does come with some baggage, which can hide some very important ideas, almost like looking at the theory with blinkers on, or studying a tree and ignoring the forest. Physical situations which seem completely different to each other can actually be identical, like we just saw with Alice and Bob. And all possible observations that can never be made will give the same results. So what is actually real? Is the wave function real? What about standard classical probability, which arises from ignorance of the true state of the universe? Is this distinct from quantum probability? And what happens when a system interacts with its surroundings? And what is wave function collapse? Well, I'm not going to answer all these questions for you, but I do have some tools to remove the blinkers and hopefully get a more complete view of the whole forest. Now, the algebraic formulation of quantum mechanics that I will mention, it's not something new. Even Heisenberg's initial formulation back in 1925 focused on operators or matrices, although it wasn't really the same thing as what I'm going to talk about. And von Neumann, in the 1930s, he hinted at this approach, although it wasn't really developed until the 1940s by Siegel. No, not you? Okay. And when it is used, the intuition is often hidden behind a load of rather dense maths, and some of its quite amazing implications and uses do not seem to be fully appreciated. Mentioning Heisenberg, this year, 2025, is the centenary of his breakthrough paper kicking off quantum theory and has been declared the International Year of Quantum. Looking at the website, anyone, anywhere can participate in IYQ by helping others to learn more about quantum on this centennial occasion. I'm doing just that. No need to even ask. I'll start with the basic formulation of quantum mechanics in terms of Hilbert spaces. I expect many of you already know this. I'm not going to go into details here, and if you're not familiar with it, hopefully you can still follow along. But if you want more information, I'll leave links in the description below and up here. So we start by representing the states of a physical system by vectors, or wave functions in a Hilbert space H. Linear combinations of these represent superpositions of states, and inner products or brackets represent probability amplitudes of a system prepared in one state to be measured in a different state. Like a spin-up electron has some chance of being measured as spin right, but probability amplitudes are complex numbers, so the absolute values of these squared are used to represent the probabilities, which are real. Any physical state psi will have probability 1 of being observed in its own state, so it's normalized. The bracket of psi, or the norm of psi, equals 1. And observables are described by linear operators on the Hilbert space, specifically self-adjoint ones, or Hermitian or symmetric, same thing. These have the property that they have an orthonormal basis of eigenvectors representing different states and real eigenvalues representing the values of the observable. For a system in state psi, an observable A can be found in any of its eigenstates with some probabilities, but the expected value has this simple form. Bra psi A ket psi. That's all we're going to need. Now that brief introduction to the Hilbert space formalism is done, we can get on to the interesting stuff. Look again at the expected value of observable A. This depends on the state psi, but in fact we don't need to use psi for anything else at all. Once we know the expected value of operators, psi and the whole Hilbert space can be done away with. It's no longer needed, and I'll show you why. Let's write P of A for this expectation. Think of P as a probability measure. It maps operators to the complex numbers and self-adjoint operators to the real numbers, their expected value. But can I justify saying that this is all that we need? Well, let's look at the ingredients of quantum theory. If we measure to see if the system is in a state phi, then the probability amplitude is the bracket of phi and psi. But probability amplitudes aren't real. We have to take the absolute value of this squared to get the probability, or equivalently, multiply by its complex conjugate. And with a slight rearrangement, this is just the expectation of this operator, ket phi times bar phi, which is the orthogonal projection onto the space of multiples of phi. And more generally, what is the probability of the state being measured in some subspace V of the Hilbert space? By the Born rule, it's the magnitude squared of the projection onto V, or P of this projection. So P is really like a probability measure. Events in quantum theory can be represented by orthogonal projections instead of sets in standard classical probability, and P gives their probabilities. But there's more. With an ideal measurement, the state gets projected onto the subspace. That's the projection postulate. Psi gets taken to its projection normalized to have norm 1. And what does this do to P? Well, it takes it to a new probability measure, substituting in, rearranging P prime of A equals P of pi A pi. Again, normalized to have total probability 1. This is defined just in terms of P. There's no need to go back to the wavefunction psi when computing P prime. And note this curiosity. This does look a lot like standard conditional probabilities. The probability of A given event B is the probability of A and B divided by the probability of B. Or if A is a random variable, the expected value of A conditional on B is the expected value of A times the indicator of B divided by the probability of B. So this looks pretty much the same if pi represents event B. So it's similar to how you update classical probabilities given an observation B, but with operators. This is curious, right? I mean, classical conditional probabilities are just a pretty basic idea. But the projection postulate is some special quantum thing, but they're looking very much the same. And moving on. What about transformations and symmetries, like translating or rotating a system or the coordinates it is viewed in? In quantum physics, such transformations are represented by unitary operators acting on the state psi. And by unitary, that means U multiplied by its conjugate is 1, which is equivalent to saying it preserves the norm of any state and is invertible. And this gives a new state, a new expected value function. But substituting in, the new expectation is the old one applied to U star AU. So we still don't have to go back to the wave function. This is determined from P alone. And what about dynamics? In quantum theory, the rate of change of the state, scaled by I(h) bar Planck's constant, is given by the Hamiltonian or energy operator. But solving the differential equation just gives a unitary transformation of the state. So aging for a time t is the same as multiplying by e to the power of minus I(h)t over h bar. You can simply differentiate this, use the properties of exponentials, and just see that it satisfies the original differential equation. Anyway, this transforms the state P like we just saw for unitary transformations. So again, it fits into our general operations on the state P. Or if you prefer differential equations, you can differentiate if you like. And after a bunch of rearranging, Standard stuff, really. You eventually get to the differential equation for state P. I, h bar, times the derivative of P of A is P of the commutator of A and H. So all of quantum physics can be done entirely in terms of P instead of psi. But there's more. What if we don't even know what state the system is in? Maybe we just have a probability distribution over states. Maybe someone comes along, tosses a coin, puts an electron in the spin-up state if it comes up heads, and spin down if it's tails, then leaves, so we don't know what they did. The electrons either spin up or spin down, but it's random, and not a quantum superposition either, just classical uncertainty. So we need to combine quantum mechanics with classical probability. But our formulation handles this, no problem. Suppose a system is in state psi, but we don't know what psi is. Say it's equal to psi1 with some probability p1, and psi2 with probability p2, and so on. The expected value of an observable A will be the expected value using state psi1 multiplied by the probability that psi equals psi1, plus the same for psi2, and so on. Rearranging gives the sum of probability pk multiplied by the expected value of A in state psi-k. Okay, so far so good. States like this combining quantum with classical probability are called mixed states, as opposed to those coming from a single wave function which are called pure states. But all the other operations of quantum theory apply to mixed states like this just the same as for pure states. Let's look at the probability of a projection, pi. It's just its expected value, so follows directly across to mixed states by definition. And the effect of unitary transformations also follows across by simple linearity. The projection postulate, that's a little bit more complicated, but going through the calculation, the expected value of A conditioned on measuring B multiplied by the probability of B is linear in the probabilities. So it also applies to the mixed state in exactly the same way as for pure states. Again, the point is that this expected value function P describes everything about the state that can ever be measured. Even mixing classical with quantum probabilities in this way, P encapsulates all physical properties. Now comes the really fascinating part. Back to our story. Recall that Alice prepared an electron in the spin-up or spin-down state. On the toss of a coin, if it came up heads, she put the electron in the spin-up state, and if it was tails, she put it spin down. That's it. No quantum magic. Also Bob. If he got heads, he prepared an electron in the spin-right state, and for tails, he put it as spin-left. That's it. 2 electrons, one from Alice, which is either up or down, and one from Bob, which is either right or left. So 2 different situations with 2 electrons. Regardless of whether they got heads or tails, their electrons were in a different state from each other. But how do we tell the difference? If we forgot which electron is Alice's and which is Bob's, what practical way exists of distinguishing them? Well, suppose we measure spin along the vertical axis. With Alice's electron, we measure it to be up or down, depending on how her coin landed, so 50% chance of either. Bob's is spin right or left, but either of these is a superposition of up and down, with probability amplitude 1 over the square root of 2. So again, 50% chance of measuring up and of measuring down, independent of how his coin landed, just the same as for Alice's electron. But for different reasons, whereas the randomness in Alice's electron is due to how her coin landed, classical uncertainty, Bob's is coming from quantum superposition. But the result is the same in either case, 50-50 of measuring up or down. This does not help to tell them apart. Well, how about measuring along the horizontal axis instead? That doesn't change anything. It's the same situation with Alice and Bob's roles switched, and we still get 50-50 chance of measuring either spin. Okay, so Alice and Bob's electrons, while they're clearly different, simple spin up and spin right measurements does not tell them apart. What about other measurements? Well, let's write out the state in the form of the expectation operator. Starting with Alice's. is half spin up state plus half spin down. And Bob's is half spin right plus half spin left. A similar idea, just right or left instead of up and down. But we already know left and right spins are superpositions of up and down, so let's substitute this into Bob's state. Expand out using linearity of the inner product, just simple algebra. We get some cancellation of cross terms, so let's remove these. And these diagonal terms can be combined, and we arrive at exactly the same thing as Alice's state. But remember, the state, or expectation operator, incorporates everything that can ever be measured on a system. So Alice's electron and Bob's, despite always being in different quantum states from each other, have identical statistical properties. No physical measurement or operation can ever tell them apart. Even if Alice and Bob repeated this, producing a whole load of electrons, so we can make lots of different measurements on them, there's no test, statistical or otherwise, that can tell any difference between them. Let me focus on this point for a moment. It's quite astounding. There's the idea that if two different states of a system are indistinguishable, if you can never tell them apart regardless of what we do, how we interact with it, and regardless of any advanced future technology we might use, if physical laws themselves say that they can't be told apart, then they're the same physical state. And if you subscribe to this idea, then Alice and Bob's electrons are in the same physical state, despite differences in their description. And you might have been told that, according to quantum theory, positions of a particle, or its momenta, or its spin, these are not physically real until measured. All that's real is the wave function, describing probabilities. Well, by the same logic, the wave function is not real either. And here's another curious thought. You have probability, standard, uncertainty, a classical idea known about forever. Then we have quantum uncertainty, something entirely new when it was discovered 100 years ago. But when you mix the two types of probability together, classical and quantum uncertainty, they can't be then separated, at least not in any unique or canonical way, so we don't know if the electron is 50-50 up or down, or if it's 50-50 left or right. And here's the third idea, maybe less interesting philosophically, but practical. If we have a quantum system in a random state represented as a probability distribution over all possible wave functions, this is very wasteful. Different distributions represent the same physical state, and we get a massively more complicated representation than is actually needed. So a more economical distribution is required, like with density matrices, which I'll get to. Maybe this point is a little less interesting than the others, but also maybe more important. Back to the formula for Alice and Bob's electron state. Although they look different, we saw using a bit of algebra that they are actually the same. But maybe you noticed already, they have to be the same without even going through the algebra. This is just the trace of operator M in the up-down basis, and this in the left-right basis. Or any basis, it doesn't matter. The trace of a matrix, the sum of its diagonal elements, is independent of basis. So of course, Alice and Bob's states are the same. They're half the trace of A. Any basis could have been used. In fact, don't even choose a basis. Just average over all possible unit vectors, the same thing. So the states just discussed are actually very common and naturally occurring, not just some contrived setup. Take an electron at random if we don't know its spin and the situation is entirely symmetric, so there's no magnetic fields or anything causing spin to align in a specific way, then the electron spin would have to be modelled exactly as described, half the trace or completely random. Here's another very interesting idea that this formulation reveals. Look at the Born rule, giving the probability of a measurement, and the projection postulate. So suppose we perform a measurement, let's say it's got n possible outcomes, and represent each of these outcomes by projection operators, pi1, pi2 up to pi(n). These should sum to 1 because they represent all possible measurement outcomes. And applying p to this, using linearity, all probabilities sum to 1, as they should. Now after performing the measurement, we see outcome I with probability pi, and the system is in state capital P of I, a projection of the expectation operator. This is the somewhat controversial projection postulate, and no one seems to agree exactly what it means, at least online, and thought experiments like Schrödinger's cat raise the question of whether the cat in a box is already dead or alive, or if it's in some kind of superposition of dead and alive, which only collapses when we open and look inside the box. When does the projection occur? Well, I'm not going to tell you here, but our algebraic formulation has a lot to say. It's quite enlightening. So back to our measurement. One of the n outcomes is observed, outcome I with probability pi, and the system is projected into this state, capital P of I. But suppose I haven't looked at the result yet. Or maybe you've looked, but I haven't, so I don't know the outcome. How can this state of affairs be represented? How can I do that? Well, there's classical uncertainty, and we know how to represent this in our formulation. You just sum each possible state or expectation operator times by the probability that that state was measured. So you average over states, and the result is a mixed state, even if we started with a pure one. And with a bit of cancellation of probabilities, we get this nice form. Now this breaks the measurement into two different theoretical steps. Step 1, you replace the state by this new state. It's projected into the sum of all possible outcomes, so nothing is yet observed, but there could be a physical effect from this change of state, and this is the part where you might say that measurement has affected the system. It's in a different state from before the measurement, but it hasn't collapsed, not as such. It has not affected the probabilities of anything which commutes with the measurement projections. If operator A commutes with the projections, then P prime of A equals P of A. And there's no funny influence at a distance yet. Not in terms of P. If Alice and Bob are measuring different systems, maybe far apart, then Alice's measurement hasn't affected anything about Bob's because they would commute. But this state still contains some weirdness. If we believe this was an objective state of the universe, then Schrödinger's cat in a box would still be in a weird position of neither dead nor alive. Then the second step of projection postulate is to replace P by its projection onto one specific observed outcome. This is important. It's the point where we observe which outcome actually happened. But it has no physical consequence. It's just the same thing as classical conditional probability, so it's not really quantum at all. It's just a subjective update of the state based on knowledge gained. So measurement has two effects, a physical effect on the state and a subjective update to probabilities, which are nicely separated out in this formulation. Okay, so I was going to talk about how this can be done in an entirely abstract way. So you get a star algebra of operators, and you get a state P on these operators, which assign a real number or expectation to each of them. And you can do this and get rid of the Hilbert space completely. Now, I did plan on putting that in the video, but when it comes to it, it's getting a little bit complicated. I think we've had enough. So maybe for a future video. But there is a happy medium between only looking at pure states, wave functions or states in a Hilbert space, and the full abstract theory of states on star algebras. And this is the theory of density matrices, defined on a Hilbert space. These describe mixed states, so it's general enough for statistical mechanics, thermodynamics, decoherence, and for Alice and Bob's electrons. And it's actually, this goes all the way back to almost the very start of quantum theory, being described by von Neumann in 1927. So let me explain. Let's start with a state psi. The expectation operator of A is bra psi A ket psi. And then let's choose an orthonormal basis. U1, U2, U3, so on. So we just plug these in and rearranging, we get this expression for the expected value of A. And it involves this operator, the inner product with state psi multiplied by psi, and a sum over basis vectors. But this sum over basis vectors, this is just a trace, which is known to be independent of the choice of basis. So the expected value of A is the trace of this thing multiplied by A. And if we have a mixed state, then we can sum over all the pure states multiplied by their probabilities. This gives the trace of this operator multiplied by A. We shall write this as rho, which is the density operator or density matrix. So the expected value of A is the trace of A multiplied by rho. And this product can be written either way round by the properties of traces. Or you can even take its square root to have a more symmetric expression if you like. That's it. Instead of vectors in the Hilbert space, we have density operators acting on the Hilbert space. So wave functions are out and density matrices are in. And to make sense as probabilities, rho has to be positive semi-definite, so the expected values of positive operators are positive, and it should have trace equal to 1, which is the law of total probability. And that's enough. Any such density operator can be diagonalized, showing that it is indeed a mixed state with respect to some orthogonal basis. In finite dimensions, this is just diagonalization of Hermitian matrices, and I'm avoiding the technicality of infinite dimensional spaces here. So let's look at a simple case, a two-dimensional Hilbert space representing a single qubit, choosing some basis rho as a 2x2 matrix, and its Hermitian, so that the diagonal entries are real, the bottom left is the conjugate of the upper right, and its trace is 1. So the sum of the diagonal entries is 1. Taking out a factor of a half, they can be written as 1 plus x and 1 minus x. And to be positive definite, the determinant should be non-negative. Computing the determinant, 1/4 of 1 minus x squared plus y squared plus z squared. So x squared plus y squared plus z squared should be less than or equal to 1. The density matrices for a single qubit form a unit ball, and its surface, the unit sphere, where the determinant is 0, represents the pure states, and this is called the Bloch sphere. So all the terms in the interior are mixed states, and all the terms at the edge are pure states. And we can see every pure state is then given by direction in three-dimensional space. This nicely corresponds to the spin of an electron. In an appropriate basis, these directions correspond to the electron spin being in that direction, and antipodal points of the sphere represent orthogonal states. Spin up is the North Pole, spin down is the South Pole, spin right is a point on the equator at the right-hand side, and so on. And if the spin is in one direction, but we measure in another, then the probability that it's measured to be positive spin in that direction is the trace of the product of these two density matrices. And working this out, half of 1 plus the dot product of the directions, or 1 plus the cosine of theta, or cosine squared of theta over 2. So the probability of spin up being measured as spin down is 0, and being measured as spin right is 1/2, as we already saw. Now looking at Alice's electron, this is half of the spin up and spin down states. So it's 1/2 of the north and south pole, which is the centre of the sphere. And Bob's is half of spin right and spin left, also the centre. So again, they represent the same state, which is the centre of the sphere. And at any point in the interior of the sphere, we see that it can be written as a convex combination of 2 points on the sphere, so it's a mixed state. But it can also be represented in combinations in lots of different ways. And this is always the case with a mixed state. There's always lots of ways of writing it as a combination of pure states. It's impossible to disentangle these classical probabilities from the quantum ones in any unique way. And then think what happens when we measure the spin along any direction. Well, it projects it to either positive or negative spin along that direction. So one of the two antipodal points on the sphere along that direction. But if we perform the measurement and do not observe the result, then it's a combination of those states. It's projecting the state onto the diameter joining the antipodal points. And this is effectively what happens when the system interacts with its environment. It gets projected onto a diagonal. And multiple interactions along arbitrary directions will quickly move it towards the center of the sphere. This is decoherence, where over time, quantum systems will move towards a maximally random state, blurring the distinction between classical and quantum probabilities. Now, this is just a simple qubit. More complex systems following some dynamics will still be affected by decoherence, but the final state could be more complex, like a Boltzmann distribution described in terms of the Hamiltonian H. Well, that's about all I have for today. There was a lot more I could have talked about. The general formulation of quantum mechanics in terms of star algebras is fascinating, putting both quantum and classical probability on the same footing. And then there's free probability, which uses this idea of states on star algebras and relates to random matrices, with cool results such as Wigner's semicircular law. All stuff for future videos. For now, I think the idea that once you mix classical and quantum probabilities together, they can never be disentangled is pretty thought-provoking, as is the fact that different descriptions in terms of wavefunctions are actually identical physical states, as illustrated by the Bloch sphere. Please like and subscribe. As for me, I've got more videos in mixed states just waiting to be observed, almost surely.
Oh yeah, I'm almost sure.